Okay guys, two-dimensional dynamics. What we're going to do first of all is just talk about obviously two dimensions. You will have forces that are being applied at an angle. That's all it is. So like when we're doing the push a desk horizontally, it's one-dimensional left and right. When we're doing the elevator shafts and the cable goes up and down, it's one-dimensional vertically. So now we're going to just combine the two dimensions and we'll have, of course, two-dimensional dynamics. So you're going to have to incorporate angles, okay? So just a nice little review. You're going to draw a Cartesian plane. We're going to use, just to remind you how this process is done. Okay, so we are going to use the same process as your math class, where on the eastern horizon you'll have 0 degrees, and then you rotate counterclockwise so that north is 90 degrees, west is 180 degrees, and then south is 270 degrees. This is your they call this rectangular coordinate system. Okay. So for example, if they give you an angle of 120 degrees, where would you be? Let's say that you're trying to pull like a wagon. You ever pulled a wagon and the handle is like at an angle and you're pulling the wagon? The wagon only moves left and right, but your force applied is at an angle to the horizontal. So imagine you're drawing like a wagon handle here. And they told you that it had a rectangular coordinate system of 120 degrees, like this. So when you go to analyze this force vector, you have to break it down into its x and y components. You guys are familiar with this. Now, which angle do we use when we do this? Do we use 120? Or should we use the acute angles in a right angle triangle? And which direction do we make it? Do we make it with the x-axis or the y-axis? X. So you'd want to draw a couple of vectors like this. And I'll just draw them tail to tip. I'm going to recommend 100% of the time that you make your angles with the x-axis so that you'd have some reference here. So what would that reference be? Because if this is 120 all the way around, you'd have a 30 in here and therefore 60 in here. So please use the angle made with the x-axis. And that's going to be critical to your survival here. Because if I want to solve for, say, the vertical component of this and the horizontal component of this, I can remember that x always will be the cosine of the angle multiplied by the hypotenuse. So let's say the hypotenuse, let's just say HYP. And that will solve for x. That will always work like that. You can always remind yourself that cosine goes with x and sine goes with y. Okay? And it's always multiplied by the hypotenuse. Whoa. So hypotenuse times the sine of 60 will equal the y component. Because if you don't use 60 and you use 30, then the sine will actually give you which one? It flips. Because what's opposite 30? It would be the overness. Okay? And then the cosine, which is the adjacent, would give you the up, which we don't want to do. Okay, this y value, you'd have to use cosine, which I don't want you to do. And this x value, you'd have to use sine, which I don't want you to do. So do not make your triangles with the y-axis. Is that clear? Okay, so let's do another one. Let's do one where they gave you the navigator method. So let's say they gave you a bearing of 120 degrees. Where do bearings start? Yeah, they start north at 0. In math class, you start east at 0 and go counterclockwise. So math class, this RCS, it's east at 0 and then counterclockwise, and you go this way. That's important in math class, and that's what I want to be consistent with. However, sometimes in your workbook, they give you bearings. So where would a bearing of 120 be? With north being 0 degrees, east being 90 degrees, because you're going to go clockwise with bearings, south being 180. So which quadrant are we in if we're doing a bearing of 120? West would be 270. So which quadrant if it's 120? So you got to start at north and go 30 degrees past. So you'd have some force vector like this. That's 30 degrees past 90. So again, you have the option. Do you use 30 with the x-axis or 60 with the y-axis? And that's going to be critical, because if you use 30 with the x-axis, then the formulas that I gave you at the beginning of the year will always make sense. This will be hypotenuse times cos 30 to give you the x component, and for the y component, it's sine. Always. Hypotenuse times sine 30 for the y, hypotenuse times cos 30 for the x. And the hypotenuse will always be the force. The hypotenuse is the force that we're going to be talking about. So if I pull a wagon at like 10 newtons at an angle of 30 degrees to the horizontal, then I can think about the situation like that. So I'm pulling a wagon 30 degrees to the horizontal. The force is me pulling the wagon through that angle. And in order to solve any style of question, you would have to resolve this force into the x and the y. And I'll explain why on the next page. So that's a nice little review of angles. So let's try and add some vectors. Call this one adding vectors. And when we add vectors, we do tail to tip drawings. But I'm going to give you an example where a tail to tip drawing is going to take a lot. I'm going to give you an idea where there's 5 vectors, and you'd have to like draw 5 of them, and it would just get confusing. Okay, so we have a pack of dogs or a pack of wolves, and they are exerting a force on a dead carcass in all different directions. Try to imagine that. A pack of wolves are exerting twice, that's odd, are exerting 5 different forces. Upon the carcass of a dead animal. Which weighs 100 kilos. So I'm going to draw a top view if you were like in a helicopter looking down at this situation. So you have the animal, the 100 kilo animal in the middle here, and then you're just looking down like from a helicopter, and you got these 5 wolves pulling in different forces in different directions. So one guy's pulling at 20 newtons at 90 degrees. Another's pulling at 30 newtons at 45 degrees. Another's pulling at 25 newtons, 0 degrees. One of the stronger ones is pulling 50 newtons, 270 degrees. And then there's one guy off on the left pulling 20 newtons at 210 degrees. Okay, and I'll zoom in here so you can see it better. So you have these 5 different dogs pulling on this object. So like, what's going to happen to this object? Where is it going to go? What do you guys think? Do you think it'll end up more to the left or more to the right? Yeah, you can see that that 3 of the forces, or two of the forces are pulling right, where only 1 is pulling left. And you have like a combined roughly 30 and 25 versus like 20. So it's probably going to go to the right. And do you think it's going to go more up or down, more north or south? Just by staring at it, you can see 50 newtons south. Also, you have some south from this one here, this 210. And you have some north from up here. So it probably will end up south because of this 50 newtons. So we think it's going to be moving sort of southeast. Do you guys agree? So that's just a prediction. It looks plausible. It's no different than like if somebody was pulling on my arm this way and someone was pulling on my arm this way. Like if he's stronger, he's going to pull me more that way. That's what's going on here. But we just have 2 dimensions in play. So what you could do is you could pick up every single one of these. Whoa. You could pick up every single one of these vectors and line them up tail to tip. And it might look something like this on my whiteboard, like this, like this, like this, like this, and then sort of like this. And then we'd be interested in the displacement from the beginning. So it probably just went southeast. That's all we're really interested in. Now, I'm just going to show you how to use algebra to solve for this red arrow here. Does that make sense? Okay. Say what? If you want to draw that, that's up to you. So the question is, calculate the acceleration of the animal. Sorry, I just had to reload it because it's being stupid. Okay, so when you have a question that involves 2-dimensional vectors, you can do a tail-to-tip drawing, but with 5 of them, it becomes a little bit messy. When simply you can just use the algebra. And what I would recommend that you do is split your page into 2 sections. So you're going to resolve, actually I'll put it over here. So to do the solution, you're going to want to resolve into x and y components. And that's, in terms of like what's important in Physics 20, this is one of the most important skills that you can master coming out of Physics 20 heading into Physics 30. Is being able to understand that forces at angles have to be resolved into their 2 components. Because in Physics 30, you'll have like momentum questions where, objects are coming at different angles, and you have to be able to understand that the momentum in the x has to equal the momentum in the x on after, and the momentum in the y before is what the momentum is in the y after. And then it goes even into the next units where you're doing electricity. You have to understand these x and y components. It's so critical. And it translates into all your physics that you'll do in the future. Okay, so what I would do is I would do net force in x and then net force in y, and I have it separated. So we have, I would say this is like F net x, and then this is F net y. You have what's happening in the y direction, what's happening in the x direction, and we're talking net. Now some of these force vectors are really easy to establish right off the bat. So which ones are really easy in x? Which ones are really easy? There's only one that's superbly easy for x. Which one? The 25 newtons east. That one is so easy, just jot it down. What is that component? Because we're doing a sum of all the vector forces. So what you think of is like this symbol here. This sigma symbol. So it's a sum of all net forces in x, and one of them is positive 25. Some of you just put 25, some of you put positive 25, just whatever for your notes. Just to, we have already established that we know that the east is positive. Now, is there any other easy ones? Okay. So, which other components have a horizontal, or which other forces have a horizontal piece to it? There's, good. This 30 newtons has an eastern component to it, and this 20 newtons has an eastern component to it. So the 30 newtons at 45 degrees, how do you resolve that into its component? The hypotenuse is 30, the angle's 45, so you would write, and it's going east, so you're going to write a positive 30 cos 45. Okay, and that's because you know that that angle's been made with the x-axis, if you think of it that way. There's a 45 in there. So if it's made with the x-axis, the angle, then it's always going to be cos for x. Damn. I just want to move these over so I have more room. Oh my gosh. Technology. Okay, and there's one more. What's the other x component? The 20 newtons and at 210 degrees. So we're not going to use 210. We have to use acute angles, right? So you jump in here. Did you say 60? Oh, why? That's bad. This is 210 here. So it's 210 all the way around, so this reference angle is 30. You'd have to use 30 in there. Hopefully that's clear. I mean, if you're not in 20-1, like, I really feel sorry for you, but... And if you have questions with this, please talk to me. So 210 starting at 0 all the way around past 180, it's 30 degrees past 180. So that's why we use a reference angle of 30. And always with the x-axis, so you can get your x and y component. Okay, so if you're not clear on 20-1 stuff, you need to talk to me or get help from somebody. Use a reference angle of 30. It's just basic geometry on a coordinate plane. Good, because it's headed left, right? So we're adding all the vectors because of the sum, but when we put it in, it'll be a minus. And it'll be the hypotenuse, which is 20, and you go cos 30. And I really apologize for why it's small. So that's the third term in this sum. And we put in negative because it's going west. That x component is west. And if you want, you could even like put in, this is your fx for that one. And this is your fy for that one. And over here for this one, similar idea. You have an x component that's going to the right, and you have a y component that's going up. Okay, so let's go ahead and solve f net in x. So you have 25 plus, what's 30 cos 45? Some random number? I'm just going to give you what I got in a calculator. You guys can try it on your own as well to confirm. But I got 28.892. You got 28? Make sure your calculator is on degree mode. Did you remember to minus?
Oh, you did the entire thing? Like that's the entire thing?
Yeah, that's the entire thing. Sorry. Oh yeah, sorry, I just do that entire thing. 28.892? Okay, good. Now before we go on, is there any questions about how I set this up so that I don't just jump into the y component with you guys having some serious confusion? Okay, well let's use my pointer and let's make sure everybody's clear. Where is the 25 coming from? Right here. Where's the 30 cos 45? Over here. So that one's the eastern component of this force. The 30 newtons. The eastern component of that. So we put that one as positive. Now where's this one? So that's the negative 20 cos 30. Where's that one? Well, it's this force of 20 newtons, but we want this x component, which is going west, so that's why we label it negative. So 20 is the hypotenuse times cos 30, and it's negative. And then we sum all that, and we get 29, roughly. It's force. Yeah. Now let's do the y. Which ones are superbly easy in y? The 20 north and the 50 south. So just get those in right now. You have a 20 positive plus negative 50 plus. What other components are there? Good. You have the y component over here and you have the y component over here. Which one's minus, Hamza? Yeah, one of them has to be minus because if you look at the purple highlight, that's all the y components. You should have 2 that are positive and 2 that are negative. We're thinking of our grid like a coordinate plane cuts through that mass. The mass is at the origin. Okay, so the positive one will be, what is it? Positive 30 sine 45. Up here, this one here, it's going up. So it's, the sine gives us the y component and it's positive, right? What would you choose upward as? Negative? Why? Are you nuts? Oh, okay, yeah. So over here, this 20 newtons at the angle of sine 30 is going to be positive or negative? Okay, good. So negative 20 sine 30. Now we're going to add all that up. So I got roughly negative 19. Did you guys get that? Okay, so then now once you have that, and if you think back to our original tail to tip diagram, which is on the whiteboard, the net in the x is basically here, and the net in the y is basically here. So that's what we just solved for. We now have f net x, we now have f net y, and then we just need to use the Pythagorean theorem to get f net r and then the angle as well. And this is always the same if you follow these tips. Make your angles with the x-axis, resolve everything into their components, keep it separate, x over here, y over here, and then this always happens where you have f net r as the Pythagorean theorem for f net x squared plus f net y squared. And of course, I'm not going to be using those rounded numbers. You know, especially if you have the TI-84, where you can copy and paste. That way you ensure you have the most accuracy possible. So when I did this, I got 34 newtons. And you have to be so careful when you do this calculation because F net was negative, remember that? But when you square a negative, it always becomes positive. But in the calculator, if you don't wrap a bracket around that negative, it will screw it up for you. And the assumption is you're in Physics 20, you know how to use a calculator. And I can't control that. You're the one in control of your calculator. You need to put a bracket around a negative so that when you square it, it becomes positive. And then you're adding a positive with a positive, not a positive with a negative. So you be careful with that calculator. Okay, so we know that the overness was about 29. The downness was about 19. And then we just solved for that hypotenuse being 34 roughly. Now we also need the angle inside from the origin. You start at the origin. So don't put the angle down here or something. It's always the angle inside. Alan. And you're going south of east, which we already assumed right from the beginning. We had made a good prediction. And this formula will always be the same as well. If you use inverse tangent, it's your f net y, the opposite, divided by your f net x, the adjacent, opposite over adjacent. And that will always solve for your theta. So we have theta being, I got 33 degrees south of east. So this is the force net fully communicated. You have the magnitude and the direction. If you want to go into Physics 30, you have to know how to do this. I could give you 33 vectors and you should be able to do this. It would just take you a long time. Okay? At most, it's going to be like 3 or 4. Maybe. Like 5 here, that's a lot. But you notice that some of them were pretty easy because they were just up, down, left, and right. Yeah, so they're asking for acceleration. Thanks, Hamza. I almost forgot about that. So when you do the acceleration, I mean, it's just going to be F net divided by m. So take that net force of roughly 34 newtons and divide it by the 100 kilos. And you get the acceleration. And then you know that the direction for the acceleration will also have the same direction as the force. Okay, so the acceleration is about 0.34 meters per second square, 33 degrees south of east. Thank you for reminding me, Hamza. Okay, so we're just going to do like one more page of notes. It'll take us to about 3 o'clock, and then you'll have 25 minutes to try some of this. And I know it's Friday, and you guys want a break, but you know, there's no breaks in physics. Good point. Actually, before we move on, I'll just give you the homework that I want you to try with this style. Where did I put my workbook? Okay, so difficult questions like this, which you don't have to worry about until roughly Wednesday. I'm gonna give you a quiz like on this kind of stuff later in the week next week. So page 138, 139, 6, 7, and 8. And the only thing about those is they give it to you in bearings. So you're going to have to do some minor adjustments before you start the question. Now, for the next set of notes, this is more time. It's closer in your time frame. So stuff that I'd want you to do for Monday. This is easier stuff, and it's called resolution of forces. This stuff's a little bit easier. Especially after you've seen that question, you'll find this stuff pretty straightforward. This is when you just make a right-angled triangle. You only have two components. And let's just imagine that you have a dog, everybody's favorite dog, Fido the dog. And you're walking Fido the dog, aren't you? And maybe your Fido's so vicious he's on a chain. So there you're walking your vicious dog on a chain. And you're pulling him, so it's like you're choking him. So you pull on your dog at an angle like that. Okay, so when you want to describe what's happening to Fido, this dog, and you want to try to do some mathematics and some physics with Fido, it has to be broken down into its two components. So this, if you imagine a force along this chain or cable or rope or whatever it is, this tension force. This tension force is equal to, and you just draw the exact same picture of Fido here. Whoa. With the chain going vertically, and it's going to be smaller than the hypotenuse, and the chain going horizontally. So depending on the angle, you basically have this force broken into two components. Good. A vertical component and a horizontal component. So that's how you have to think about it. A force at an angle is broken into the two components. And those two components are smaller in magnitude than the original force because it's done at an angle. Oh, sorry. Thanks for that. This is, of course, Fx. Okay, and then do you see how I drew the two components? Is that how we draw them? Is that the proper way? What's the proper way? Tail to tip, okay? But I just wanted to show that the force at an angle is equivalent, one second there, Zach, equivalent to the, to the sum of the two components. What did you want to say, Zach?
I was wondering where you got your square dog. What store did you buy it?
That rectangular dog?
Yes.
Got him from the internet. Good question, good question. Way to keep it light. Okay, so we will do an example very similar to this. So it's roughly the same picture. And you just say a person or the chain. A chain exerts, like a person pulls on the chain, so the chain exerts a 60 Newton force, poor dog, upon Fido. Oh, Fido should have his name capitalized. We're choking him, but we'll capitalize his name. Fido the dog. At an angle of 40 degrees to the horizontal. And you'll find for the most part, except for some nasty ones in your workbook, they typically just give you the angle with the horizontal, which is the one you want. You always want the angle with the horizontal, so that you can use r cos theta for x and r sine theta for y. Okay? So Fido the dog, you could draw a free body diagram with Fido the dog. Okay, so Fido the dog. They told you that the chain was this way, so that's how you know. Oh, sorry, I'm leaning on this thing. Okay, so there's my 60 Newton. Come on. 60 Newton force. 40 degrees to the horizontal, so let's try to make that a little bit more accurate. And then what you can do, if you had different color pen or something, is you can change up the color and draw in these vectors to give you the tail to tip component, tail to tip component, and this is free body diagram. So, and if you always have it with the horizontal, you don't even have to do any thinking. This is just going to be 60 cos 40. Oh, sorry, I'll get the angle in there in that diagram. It's a 40-degree angle. So that's what's so nice about this. You don't have to do any thinking. And this one here is 60 sine 40. So let's just calculate those right away. That's what's so nice about if you draw the angle with the horizontal. 60 sine 40 and 60 cos 40. And I got like 38.6 roughly. And 46.0 roughly. And notice that those forces, like on their own, are smaller because obviously right angle triangle, the hypotenuse is the longest, etc. Okay? So that's it. That's all I wanted you to do with this question. This is called resolving into components. So if you ever see on a test or a quiz resolving into components, this is what I'm asking for. And it's the preliminary step for any sort of question involving Fido the dog. So for example, if it says, Mr. Lineweber is pulling the dog at 60 newtons, 40 degrees to the horizontal, at a constant velocity, what's the force of friction? If you ever wanted to answer that question, which component would you use? Would you use the hypotenuse, the vertical, or the horizontal component? If I'm pulling this dog and the force of friction is what I'm looking for. Yeah, you'd have to use the horizontal component because the motion and the friction would be left and right. But what if I asked what the normal force of the dog was? What component would you use? You'd have to use the vertical component. Okay, and you would only ever use this 60 degree or 60 newtons if I was like yanking him in the air at the same angle, which you'll never have that question. It'll always be like pulling the wagon or pushing the lawnmower. So you can call these lawnmower questions as well. Lawnmower question. You okay, Suad? Tired? Pushing the lawnmower. What happens when you push a lawnmower? Yeah, a lawnmower moves left and right, but the force applied is at an an angle. Yeah, all the lawnmowers have that, you know, like a piece of metal at an angle, right? Okay, so I think we'll leave it there. And the homework that I want you to try that's really straightforward is in this 4.2 section. And you're going to find it very simple because it's just tail-to-tip drawings and like Pythagorean theorem. So your homework for the weekend is reviewing one-dimensional dynamics on page 100. You remember that? And the homework for this section is page 115, 9 to 14, 9 to 12. Okay, so only 3 questions for the new stuff. If you really want to challenge yourself, try the questions that were given about 10 minutes ago on page roughly 138. And then you also have your review for one-dimensional dynamics on page 100. Okay, so you have till the rest of the class to do some independent study.